Hello guys, in this video we will start to study an object's motion in 1D. Or kinematics in one dimension. Alright, so let's recall what we discussed in the previous chapter. We talked about some key variables we need for describing an object's motion. So those are the position r, the velocity v, and then the acceleration a. Then we talk about all these instantaneous quantities at a certain instant, a certain time instant, t. Now, since these are like three-dimensional vectors, but now we are confined in the 1D motion, so we don't actually need all the components of r. So r, remember, is given by xi hat plus y j hat plus z k hat. So these are the three independent components of the position vector r. But now we're confined in the 1D motion, so we just need this component. So it suffices to just talk about the position vector with the x, okay, with the x component. And you may ask that now we have kind of like a pure number, and how do we represent the direction of this quantity now? Right. So the answer is that the direction of the vector is actually included in the sign of this position vector x. So if x is positive, then that means that the object here is to the right side of the origin. Now here's the picture. So now let's say I have a one-dimensional space, meaning the object only lives in this line, right? It can only go back and forth or along one direction, right? Along this straight line. And the origin O is here. And if x is positive, that means that the object is at this side, to the right side of the origin. And if you want to draw an arrow for this object's position, then it would be just like that. That's the position we previously called r. Okay, so that would be the position vector r. And if an object is, if the x here is negative, then it's to the left of the origin. So if I draw, let's say, a position here, that x is negative, then I can draw an arrow starting from the origin, pointing toward this point, this negative x point, and that represents this position vector r, which is negative, in the negative x-axis. And this position vector is pointing along positive x-axis. So that means that in 1D motion, the representation of the object's position simplifies to just a single x here, and the sign of the x will represent the direction of this object. Okay, so that x already includes both magnitude and direction. Okay, so that's the simplification I want to mention for the 1D motion. And for the velocity, it also simplifies. So let's see the velocity now. Previously is vxi hat plus vy j hat plus vz k hat. Okay, so now we can totally neglect the last two components because there's none such components. The object is along the x-axis. So that's only Vx. And if I want to draw the velocity, let's say when the object is here, and I want to draw the velocity at this instant, then I'm going to use a different color. So let's say the object is moving at this position right now, but it's moving to the left. So the velocity is this way. So that would be Vx. Okay, Vx pointing to the left. That would mean this Vx is negative. In this case, it's negative, right, because it's pointing to the left. And similarly, if I want to say I want to also represent the acceleration a, then I only need to consider the x component, just this component. So now let's say this object right now is accelerating to the right. Then at the same location, I can also represent this object's acceleration. I'm going to say ax, like that. Okay, and that will be positive because it's along the positive x-axis. So ax will be a positive number pointing to the right. All right, so that's the several vectors in 1D. They simplify to just its x component, and then later on we just focus on the x component. Okay, so let's move on to some diagrams. And I will start with the xt diagram. Or you can say it's the position time relation diagram. And usually people will draw this kind of coordinate system. So that's this x-axis and that's this t-axis. The origin O is here and that's x-axis. So that drawing will give you the correspondence of the position with the time. So now let's say when I draw this kind of curve, this kind of motion, I have such a curve, let's say. And if I look at one instant, let's call this ti, some instantaneous instant. Then when I look at this point here, it's intercept with the x-axis. So I draw a projection there. Then that length will represent this object's position at this instant. Let me call this xi. And similarly, I can have some other instant, let's say this t final, okay, final instant. And the correspondence of that instant in the vertical direction, in the vertical axis, is the x final. So this curve gives us a relation that can, in some sense, can be used to extract the information about this object's motion, right? Because as we discussed, now we know xi, ti from the diagram, and then we want to study how this xi evolves to x final in a time interval that goes from initial time to the final time. So now the question is, what is V average? And in fact, this one is the Vx average, right? Remember, we are talking about 1D motion. So that, according to the definition, is given by delta x over delta t, which is x final minus x initial over t final minus t initial. So I already told you that I want to talk about the xt diagrams, some diagrams in 1D motion. So let's think about also how to represent this average velocity in diagram. Can I represent that in the diagram? So the answer is from these two differences. So we have the position difference, which we call displacement. And that can be represented in the picture, right? Because I already know x final is this length, and x initial is this length. So if I do the subtraction, so that's the initial position, and here's the final position vector, right? So when I do x final minus x initial, remember the rules we talk about for vectors subtraction. Of course, in 1D, it simplifies. You don't necessarily think of that. You probably know already it's this length, right? But if I use the vectors subtraction rule that we talk about, then there will be the direction will be finals. We will draw an arrow starting from the second vector, which is xi, its head pointing toward the first vector in the subtraction x finals head. So that is delta x. That's delta x vector. Now delta t is simply just a pure number, which is a scalar difference. And delta t is given by this length. Okay, so let's put them together and then see what we get. So in order to put them together, I want to move them to this new location here, and that will still represent delta t, right? I just move it parallelly upward. And also move this delta x parallelly to the right side. Then I put it here, put it this side. And they form a right triangle. So here's 90-degree angle between these two lines, okay? So when I do delta x over delta t, this ratio here, it will represent the tangent of this angle. Let me call this angle theta. So that will give us tangent theta. Okay, so think about again the right triangle. And this tangent theta in mathematics is called slope. It's called, in this case, it's average slope. So that's the slope definition in mathematics. You use the difference in the vertical direction divided by the difference in the x direction and then horizontal direction, and then you get the these angles tangent value, and that's called a slope. Okay, and its direction is along this way, right, along that. Sorry, it's determined by this angle, the tangent of that angle value. So that's what we will do in the future. So the average velocity is the slope, average slope, right, of a curve. And in the limit of delta t goes to 0, or you can say t final approaches t initial, right, in this limit. So this point approach that point, this point approach that point, then we get instantaneous way. And we call it dx dt previously. Okay. Now, in terms of the angle, it's still called tangent theta, and it's still the slope. The name is still slope, but this slope now is the instantaneous slope. Now, in order to draw a better or a clear picture, let me redraw this xt diagram. Okay, so now I'm looking at, let's take one point here. That's some kind of instantaneous point I'm interested. Then I'm going to draw a tangent line. So let me write down here. How do you draw the slope? The slope here is tangent line to the curve, to the xt curve. And these tangent lines, how do we define this angle theta here? Now we only have 1 point, right? We don't have 2 points to determine the angle. But now we can actually generalize that. So the angle here is defined as by extending this line, then it intercepts with the x-axis, not x-axis, the horizontal axis. And this angle is the angle theta. So that's this angle theta here. Okay, so that's the definition of the slope in mathematics. So now let's look in detail the theta angle. Theta angle is with respect to the horizontal axis t. Now in this case here, this angle is less than 90 degrees, or an acute angle. Theta is less than 90 degrees. Then tangent theta is positive. And that would mean Vx is positive. Meaning at this instant, the direction of the velocity is along the positive x-axis. Or you can say the object at this instant is moving toward the right side. Moving to the right. Now how about the other case? Let's say theta is less than 90 degrees. The answer is that now the velocity will be negative. So let me show you this negative velocity situation. So let's say this object, now the curve will go down like that. Okay, so we're talking about some general property, general motion, and then it could happen like this. So now if I look at the slope, let's say at this point, and let's do the extension to the t-axis. Now this angle is the theta at this instant. Okay, so that theta angle will be greater than 90 degrees. So in this case, the tangent theta will be negative, which will mean Vx is negative, or the object is moving along the negative x-axis. Or you can say the object is moving to the left. Now how about some special angle? I'm running out of space here, but how about theta equals 0 degree? I haven't talked about that before. I talked about the less than 90 degree. So that will happen here, right at the top. Right here. And this angle now will be, for the slope, will be 0 degree, and then the velocity will be 0. So at this instant we have tangent 0 degree equals 0, so the velocity equals 0. So now at this instant the object simply just stops without doing any motion. Okay. Now, how about another special case if the theta here is 90 degree? Can that happen? Because we know the property of tangent function, in this case, tangent 90 degree equals infinity, right? So that would diverge. So in reality, that could not happen because we know even the speed of light has a limit, right? 3 times 10 to the 8 meters per second. We cannot have infinity as the speed. So that would be unphysical. But reflected in the diagram, it would be something like vertical. You have a vertical line. So let's say I continue this and then go up vertically. Then that would be the 90 degree angle for the slope. But again, that's unphysical. This one is unphysical. All right, so now let's continue with the diagram. Let's talk about the VT diagram. Now in 1D, we just need to draw Vx and T's relation. And also notice just one side note that I do not draw like on the left side here, because for all physical time, the time must be positive. We cannot have a negative time. Okay, so that's why we confine with the right side. And let's say we have a curve that looks like maybe like that. Okay, that's the Vx curve. Now similarly, the slope of this Vx would be acceleration A equals dVx dt, and that's the slope. So I can draw at least instant a slope, and that would represent Ax equals this tangent value of this angle. And then we have similar discussion. Now in this case here, the angle is less than 90 degrees, so the object's acceleration is to the right. It's moving along the, it's accelerating along the x-axis, positive x-axis. Okay. And then another point, let's say here, then we have starting to have a negative A. All right, so that's the VT diagram. The AX here is again the slope of the VT diagram. Now, how about the XT diagram? When we talk about XT diagram, we said that the slope gives us the velocity. Right, so here's the 1 instance slope, and that would be Vx in this case would be positive, right? At least instant 1, okay? And let me call this Vx1. And I do the same thing, let's say here, at instant 2, again, I draw slope, then that would be Vx2. Now in this case, it would be negative, right? Because the slope is, the line is pointing toward left, and then that would mean the slope is negative. So now the question is, can I get acceleration information? Can we get acceleration information from the XT diagram? Okay, so the answer is yes, because now I know the velocity here is positive, and then later on is negative. So that's a transition from a positive to negative velocity. So at least I can say the acceleration, the average acceleration, is delta Vx over delta t equals Vx2 minus Vx1 divided by T2 minus T1. At least I know this Vx2 minus Vx1 is negative. So the average acceleration at inside this range, right, in this time interval, should be negative. So that means that the average acceleration is pointing to the left, right, to the negative x-axis. In fact, this relation will hold in the limit of t goes to delta t goes to 0. So the acceleration here, instantaneous acceleration here, which is dvx dt, in this case here will hold, meaning at all these instants in between this average velocity, in between these 2 points, it's always true. Its ax is negative, which is always true. And that is the so-called convex curve, because it's pointing upward, right? Bulging upward. It's bulging upward, so it's called a convex curve. And you can also say it's curving downward, right? The whole curve here, the whole time interval here, the curve is downward, curving downward. Then we have the property that the acceleration inside this curving convex curve is always negative. Okay. Now what happens if the curve now goes up like that? Now it's curving up or concave. Curving upward. Then we say this ax is always positive in this case. So you can also do the same thing like I did here. The velocity is negative at the beginning and then later on is positive. So the change of the velocity is positive. So let me put down this ax direction here. So ax is always positive in this part of the diagram. And ax is always negative in the previous range. So that will inevitably point to the transition point. So at this transition point, ax equals 0, meaning when I take the derivative dvx dt, it becomes 0 here. And that's the transition point for concave and convex part of the curve. All right, so that's the property of the several diagrams. And with this kind of diagram, we can actually know more about the object's motion. Now, these are just like purely math. So we have ax direction, velocities, etc. But we actually haven't talked about their meaning for the object's motion. So let me continue with this discussion, and let me call this speeding up or slowing down. Okay, so these two words are like everyday language. When you describe an object's motion, you will say this object speeding up or slowing down. You will say that, right? So that's why let's give them some definition in physics. What's the meaning of speeding up? Okay. So the speeding up is this situation when the velocity of the object is parallel to the acceleration. Now reflected in the diagram, you will say let's say that's V, and that's A. Okay, they're pointing in the same direction. Then we say the velocity will become even larger later on. The next instant V will be greater than the previous instant V. So this object is speeding up. Okay, so now why is that? So mathematically, we know the A here is dv dt. So I can actually, maybe a better way of representing this is by looking at the small time interval. So delta V equals A times delta T. We're looking at some tiny delta T. Okay, so we have that. And then delta V here is V final minus V initial. Therefore, the final velocity is initial velocity plus AT. So if these two quantities, V and A, they're in the same direction, they're parallel. So the V here, I mean, is VI, the initial velocity that you started with. Then V final, its magnitude must be greater than the initial velocity's magnitude, right? Because they have the same direction, so they will add up. They will add up in the or we add up these two vectors. So that's why it's the speeding up case. Okay. Now slowing down, as you probably guessed, they will be in the opposite direction. So I'm going to call it anti-parallel to A. Okay. Now reflected in the diagram. So now let's say here is V, then A is the opposite. Okay. Now according to that, this final V will be less than initial V's magnitude. So that's why it's the slowing down. Okay, so now let's combine this with the curving up and curving down picture that we talked about for 1D, and let's kind of apply this understanding to those XT diagram, and let's see, can we extract some information about this object's motion. So here's the diagram, curve down and then curve up and then going on. Okay, so let's see, let's divide this object's motion into different time intervals. So I'm going to talk about before this highest point, before the peak, and also here, and also the transition point. Okay, and the lowest point, the transition point. So now we know, we already talked about like curving down or convex. This A here will be negative. AX here will be negative. And at this point, A equals 0, exactly at the transition point. Now at this range, before the next transition point, AX will be positive because it's curving up or concave. And we also know how to identify the velocity direction by looking at the slope. So let's pick a point here. So this V is positive. Okay, and so let me actually label this as instant. T1 and instant T2, instant T3, instant T4, and that's the instant 0. Okay, so let's talk about between 0 to t1 instant. Now in this range, the velocity is positive and acceleration is negative, as we already know, right? It's curving down. So that fit the definition of anti-parallel V and A. So the object is slowing down in this range of time. And then if you draw the velocity at the top, right at the t1 instant, okay? So we know the velocity here will be 0, right? So and slow down until Vx1 equals 0. So that refers to the t1 instant. The velocity will be 0 here, right at here. Okay. Now let's draw the slope between t1 and t2. Now this slope is negative. So between t1 and t2, Vx is negative, Ax is negative. So now they're in the same direction. They're parallel, right? So that means that the object is speeding up. So the next instant velocity will be greater than the previous instant. Until t2, the velocity will be maximum. Until maximum speed at t2 instant. Okay, so v2 here will be vx2 will be max in this range. Now t2 to t3. Let's keep drawing the slope. Now this vx will be negative. Within this range, vx is negative. Now ax is positive. Okay, so again we're at a range of time that the object is slowing down. Okay, until this instant, the t3 instant, you draw a slope here, the velocity will be 0. Will be 0 again. Okay, so until Vx3 equals 0. Now we can continue this discussion. Let's say I draw a slope between t3 and t4, then that velocity will be positive again. Ax will also be positive, and then we have a speeding up situation again. Until this transition point t4, until maximum speed at t4. Okay, so basically that's the meaning of the several diagram. XT diagram is especially important. Sometimes when people talk about XT diagram, you can actually extract a lot of information from it. Okay, and also XT diagram is the natural diagram to draw because when people measure an object's position, they will put it in a coordinate system. So the coordinate system they put in is the x versus t, the position versus time. Okay, so that's why it's super important that you understand the meaning of this XT diagram and also what kind of information you can extract from such a diagram. Okay, so that's all. And next time we'll talk about the opposite direction. How do you go from acceleration to velocity to the position? All right, thanks for watching.